only methane does not show intermolecular hydrogen bonding or PD-PD attractions. This means then you have to say that hydrogen bonds are stronger than London dispersion forces, significantly stronger than London dispersion forces. Only ammonia, water and HF show intermolecular hydrogen bonds, while methane has only London dispersion forces. Thereby, methane should show the lowest boiling point because methane has the weakest intermolecular attraction forces. Then we have separated methane. Then compare ammonia, water and HF. Then all three are qualified for intermolecular hydrogen bonding. Then strength of an individual intermolecular hydrogen bond will be governed by the net electronegativity difference. If we take OH bond and HF bond, OFH, we'll take other one NH. Here, according to Linus-Pauling scale, here electronegativity of hydrogen is kept constant here. Electronegativity of nitrogen is roughly 3, oxygen 3.5, fluorine 4. In the same order, electronegativity difference increases. Here 2.1 and 3.9 is the difference for NH, oxygen 2.1, 3.5, 1.4 is the difference, fluorine 2.1 and 4, then 1.9 is the difference. So electronegativity difference of NH bond is the least, HF is the highest, OH is in between. In the same order, the strength of an individual hydrogen bond increases from NH to HF. One factor is that. The other factor is the average number of H bonds per molecule which can be formed effectively. When we take HF, there are 3 non-bonding pairs per molecule. When ammonia is taken, only 1 non-bonding electron pair per molecule in the valence shell, but there are 3 NH bonds. In HF, only 1 F bonded hydrogen is there. Now, in order to form a hydrogen bond, we'll take HF here. In HF, one of the lone pairs of fluorine should interact with another fluorine bonded hydrogen of another molecule. Now, the number of lone pairs and number of H atoms bonded to the highly electronegative atom should be used in 1:1 ratio to form these intermolecular hydrogen bonds. For example, we'll take 100 HF molecules. When we take 100 HF molecules, there are 300 lone pairs. 300 lone pairs are there, but only 100 F bonded H atoms are there. When we take ammonia, if we take 100 ammonia molecules, there are 100 lone pairs, but there are 300 N-bonded H atoms. When we take water, it's a symmetrical molecule. There are 2 lone pairs as well as 2 O-bonded H atoms. Therefore, if you take 100 water molecules, there are 200 lone pairs as well as 200 O-bonded H atoms. Therefore, highest number of hydrogen bonds per molecule can be created by water molecule out of the 3 molecules, different molecules we considered here. See whether you understand that. We'll take suppose you are going to give a treat for your friends, then you arranged, we'll say 200 banana and 200 pieces of cake. In the other event, 100 bananas and 300 pieces of cake. In the other one, 300 bananas and 100 pieces of cake. Suppose each student takes a piece of cake, provided that he is given 1 banana. Otherwise, he does not take the piece of cake. In that way, even though you have spent money for 200 bananas and here in the second event, even though you spend money for 100 bananas and 300 pieces of cake, here only 100 bananas will be used with 100 pieces of cake. Then it is in vain to give 300 pieces of cake. 200 pieces will be a wastage. Only 100 pieces will be used by 100 with 100 bananas. Third one, 300 bananas and 100 pieces of cake. Then even though there are 300 bananas, only 100 pieces of cake is there. Therefore, 100 pieces will be used with only 100 bananas. Then again 200, it is in vain to give 300 bananas. It is a wastage of 200 bananas. Like that, you have to offer it with the correct proportion. In the first event, 200 bananas and 200 pieces of cake. Then each piece of cake will be consumed with 1 banana. Therefore, when the proportions are like 200, you can treat for 200 students. In the second event, you can treat only for 100 friends. In the third one also, you can treat only 100 friends. Therefore, you can treat for the highest number of friends once these proportions are equal. Similarly, in water, 2 lone pairs, if you take 100 molecules, 200 lone pairs will take lone pairs as banana. Then other one O-bonded H. Then 200 lone pairs as well as 200 O-bonded H atoms. then they are consumed in 1:1 ratio. That is effective. Then highest number of hydrogen bonds can be shown by water. In the other two, here if we take here lone pairs, here 100 lone pairs means ammonia, we'll take ammonia. Then 100 lone pairs, 300 N-bonded H. It's too much, 300. In the other one, HF, 300 lone pairs, but there are no 300 F-bonded H atoms in 100 molecules. In that way, water forms the highest average number of hydrogen bonds. Then when we take one water molecule in the average orientation, then suppose its motion is very much low, like in ice, then each O-bonded H will interact with one lone pair of another water molecule. Like that, here lone pairs will interact with H atoms of other water molecules. Particular H atom of the two H atoms of the this water molecule will interact with lone pairs of two other water molecules. So it has to fixed in a position like that to show the highest average number. Then it should be a solid. If in ice, the highest number of hydrogen bonds per molecule will be shown by water. Then you can see there are 4 hydrogen bonds, but it's debatable. Suppose you share lunch with 4 other friends, A, B, C, D. Suppose here 4 lunch packets. Even though it seems that you ate, suppose each lunch packet is 1 kilogram, then since you taste all 4 lunch packets, it seems that you have eaten 4 kilogram mass, but really it's not 4, it's 2, because you are sharing. Similarly here, even though it seems to be 4, half of the hydrogen bonding is belonging to the other neighboring molecule. In that way, somebody can argue the highest average number of H bonds per molecule of water is not 4. 4 divided by 2 equals 2. In that way, if we take ammonia, even though there are 3 H atoms per molecule, only 1 lone pair, again there are only 2 hydrogen bonds can be formed with 2 other molecules. Then if half of the hydrogen bond is belonging to the other one, if we argue like that, then 2 divided by 2, it should be 1. In HF also 3 lone pairs but only 1 H, therefore highest average number, as the highest average number, each HF will contribute for 2 hydrogen bonds, but half of each hydrogen bond will be shared by 2 neighboring molecules. Therefore some chemists may argue that only 1 hydrogen bond per molecule is there. Anyway, number of highest average number of H atoms per molecule will be shown by water. Ammonia and HF show similar highest average number of hydrogen bonds per molecule, that should be half of the amount of water. Okay. Then again, if I tell from the very beginning, all are simple molecular structures. Therefore, intermolecular attraction forces govern the strength of the intermolecular attraction forces govern the boiling points. Ammonia, water and HF all show intermolecular hydrogen bonding, but CH4 methane cannot form intermolecular hydrogen bonding. All of them show similar strengths of London dispersion forces since they are isoelectronic. Then hydrogen bonds are very much significantly more strong with compared to London dispersion forces. Therefore, the weakest intermolecular attraction forces should be shown by methane. Therefore, the boiling point of methane should be the lowest. We have to justify its lowest value like that. Then move to the others. All ammonia, water and HF show intermolecular hydrogen bonds, PDBT attractions, London dispersion forces, all are shown. Here we have to pay more attention on hydrogen bonding. Then highest average number of hydrogen bonds per molecule is shown by water here. Therefore, the overall strength of intermolecular attraction forces should be the highest in water. Therefore, boiling point of water should be the highest. Then ammonia, that is the highest, CH4 is the lowest. Now we have justified the two extremes. Thereafter we have to think of ammonia and HF. When we consider ammonia and HF, both of them should show the same average number of H bonds per molecule. Therefore, we have to think of the strength of an individual hydrogen bond. Then we have to think of Pauling's scale. Here, fluorine hydrogen electronegativity difference is greater with compared to NH polarity difference. As a result, the strength of an individual hydrogen bond is stronger with compared to of HF with compared to that of ammonia. Therefore, the overall strength of intermolecular attraction forces of HF should be greater than that of ammonia. Therefore, boiling point of HF should be greater than that of ammonia. Like that, you have to build up the answer here. Next, part B. Compare and contrast the reactions of concentrated sulfuric with solid potassium chloride and with solid potassium bromide. Okay. Now we'll analyze the question. Compare and contrast the reactions. Here the reactions. Reactions of concentrated sulfuric acid with solid potassium chloride and solid potassium bromide. Now we have to give the similarities and the differences here. Then similarities. Now you know that both hydrochloric acid and hydrobromic acids are strong acid. They undergo complete ionization in water, but here they have used solid potassium chloride and solid potassium bromide. If you have done this practical, here solid is there, you can imagine that when concentrated sulfuric acid is added, conc H2SO4, here majority is sulfuric, only small percentage of what is there in conc sulfuric. Therefore, in the final resultant system, less amount of what is there. In such a case, Cl minus and Br minus can be protonated by H plus ions given by sulfuric acid. Therefore, the first event is both halide ions, chloride, see, here I am going to give you the similarities. Both chloride ions and bromide ions are protonated. Protonation is can be regarded as a reaction. Here reaction means chemical reaction. So one thing is a protonation. So both of them undergo protonation. In the protonation, suppose you have added OH minus. If OH minus is protonated, it will not stop at the first protonation, provided that excess H plus O hydroxonium is there. Then through the second protonation, it will end up as hydroxonium ion. But here in halides, both of them undergo only the first protonation. Thereby, both of them show the respective hydrogen halides, hydrogen chloride and hydrogen bromide. So one similarity is both of them are protonated. Then secondly, the result of this protonation is both of them form hydrogen halides. Hydrogen chloride and you better write hydrogen chloride and hydrogen bromide, commonly hydrogen halide. Both of them form hydrogen halides. These are another similarity. Thereafter, we'll see what is happening. If you have practically done that, once concentrated sulfuric acid is added to hydrogen chloride, you can see misty fumes. We'll see how they occur. H plus and Cl minus bond each other to form HCl. This is an exothermic reaction. Due to the heat, you know that once the solution is heated, gas escape. Then HCl will escape. And all the hydrogen halides are highly soluble in water. You know, in our planet, in our atmosphere, there are plenty of water droplets, even though we can't see most of the time. Then HCl is readily, HCl, HBr, they are readily soluble in water. Then since the atmosphere, in our troposphere, when water droplets are there, HCl can dissolve in those water droplets. Then you can argue it is not a chemical reaction. Anyway, after dissolving HCl in those invisible water droplets, as a secondary event, it will undergo deprotonation. It will form hydroxonium ions and Cl minus within the water droplet, respective water droplets. That's a chemical reaction. If part of the HCl will remain as HCl, since a tiny amount of water is there, another part will undergo ionization, followed by H3O plus and Cl minus will be formed. That's a chemical reaction. If these reactions are occurring, you know that HCl itself is invisible. Water droplets are also invisible most of the time, if it is not a fog or mist. But when HCl dissolves in those water droplets, you can see misty fumes. That means you can see scattering of light. This scattering of light will lead, due to these reactions, their refractive indexes will be different with compared to pure water molecule, water droplet. Anyway, you can see misty fumes. So observing that misty fume will be contributed by those chemical reactions also. Therefore, that can be regarded as a chemical reaction here. Then the first one is protonation of the halide ions. Secondly, the protonation is similar, they occur in 1:1 ratio in the ions. Then both are forming hydrogen halides. Thirdly, these hydrogen halides dissolve in water droplets in the air, followed by HX will react with water to form hydroxonium and respective X minus. Then a misty fume will be observed. These are similarities. Then differences. We'll see the differences. You know that chlorine is more electronegative than bromine. That means chlorine is more greedy for electrons than bromine. If it is more greedy, after gaining the electron, after occupying the octet, after becoming the halide ion, Cl minus will not sacrifice its electron provided that a very strong oxidizing agent is not there. Okay, potassium permanganate, acidified potassium permanganate, like very strong oxidizing agents will oxidize Cl minus to Cl2. But here concentrated that means the oxidizing power of even though sulfur is at +6 in concentrated sulfuric acid, that oxidizing power of even of concentrated sulfuric is not sufficient to oxidize Cl minus to Cl2, but it can oxidize Br minus to Br2. That's a difference. Then one difference is Cl minus is not oxidized by sulfuric acid, whereas Br minus is oxidized to Br2 by the oxidizing agent sulfuric. Then you better mention the observation also. Maybe an orange or red brown solution depending on the concentration. We'll say as an average orange solution will be formed, or else you can see red brown fumes of Br2. Such an observation may be mentioned here. So Cl minus is not oxidized by conc sulfuric, one thing. Another one, Br minus is oxidized by sulfuric acid. Then the observation, red brown fumes or red brown or orange solution will be formed. Then you better explain it here. The oxidizing power of sulfuric acid is not sufficient to oxidize Cl minus, but its oxidizing power is sufficient to oxidize Br minus. Thereby Br minus is oxidized to Br2. That's the oxidation. Then if there is an oxidation, there must be a reduction. Then what's the reduction? Then the sulfur at +6 undergoes a reduction to sulfur dioxide. That's the reduction. The sulfur at +6 gains 2 electrons to form sulfur dioxide. That's the reduction. So there occurs a reduction with KBr, potassium bromide. That means in the presence of KBr, sulfuric or sulfur in sulfuric undergoes a reduction from +6 to +4 to form the choking smelling sulfur dioxide. You better mention the observation also. Here it's not a visual observation, you can smell it. It's a choking smelling, very difficult to bear it. Choking smelling gas is formed. So these are the differences between potassium chloride and potassium bromide with respect to their reactions. Then question number 17. This question is about 2-methyl-butane-2-ol and some related compounds. Draw the displayed formula of 2-methyl-butane-2-ol. Then butane means you should draw 4 carbon atoms. 2-ol, you better draw all the bonds here. 2-methyl. Then complete the other hydrogen atoms also. In the exam you have to draw each and every bond present in the molecule. So draw the displayed formula of 2-methyl-butane-2-ol. You have to draw it. Then 2-methyl-butane-2-ol forms 2 different alkenes in an elimination reaction. One product is 2-methyl-but2ene. Okay. Identify by name or formula a reagent for this reaction. So student, you have to think of what that reaction is. It's a dehydration. You can see that the water components have been eliminated. Here central OH is there. It's a tertiary alcohol. That OH should be eliminated with the aid of another H plus to form water. Then it's a dehydration. Therefore, the respective agent should be dehydrating agent. So identify by name or formula a reagent for this reaction. Then you have to write a dehydrating agent. Now as dehydrating agents, you can take different dehydrating agents. Here this is a tertiary alkyl, tertiary alcohol. Now being a tertiary alcohol, if OH is removed by protonating it, the resultant carbocation will be very much more stabilized due to the positive inductive effect and the hyperconjugation. Therefore, it can easily be protonated and OH can be eliminated. Protonation followed by elimination of water. Now OH is removed. Then you think of the alpha carbon atoms. Here 3 H atoms are there. Here 3 H atoms are there. In the other side 2 H atoms are there. Then if the terminal, that means primary, one of the primary CH bonds is broken here, then the double bond comes to a cone. But if this H is eliminated from a secondary, here this is a secondary carbon, if the deprotonation occurs from a secondary carbon, the resultant alkene will be more stable. Therefore, here they have used the most stable product of this reaction. They say one product is 2-methyl-butane-2-ene, but2ene, that is the most stable one. Other than that, the double bond may come to the cone. Then identify by name or formula a reagent for this reaction. Then dehydrating agent such as conc sulfuric, conc phosphoric can be used. Here, since it is a tertiary alcohol, it's much easier to lose the OH. Then instead of sulfuric, conc phosphoric is also better here. Identify by name or formula. Then I am going to write formula H3PO4, but conc phosphoric. or else conc sulfuric or alumina Al2O3 like reagents can be used here as the dehydrating agents. Roman number 2, draw the displayed formula of the other alkene form. Now you see, if H is, that means H plus is given by this one of the terminal carbon atoms, then a corner double bond will be there, either here or here. Then a terminal double bond should be there, say double bond C, then HH. On the other hand, CH3 and C2H5 should be there. Again, they are asking you to draw the displayed formula. Then you have to draw all the H atoms here. Okay, then this tertiary alcohol can undergo dehydration in the presence of conc sulfuric, conc phosphoric or alumina like strong dehydrating agents to form a double bond like in the printed one at the center, or else as a terminal double bond. Okay. Roman number 3, explain whether or not these two alkenes show geometric isomerism. Now we'll brush up that knowledge. In order to show geometric isomerism, there should be a restricted free rotation about the double bond or any group which resembles a double bond. We'll say cyclic group like that. Here there should be a restricted double bond here. Then there should be two different groups on each carbon of the double bond. We'll say here A, here B, here C, here D. Then one qualification has been gained by this molecule because there is a restricted free rotation about the CC bond. But see the two alkenes, in the printed one there are two identical groups, that is CH3 groups at right side. In the other one there are two H atoms on one carbon, on the same carbon of the double bond. Therefore both of them cannot show geometric isomerism. Then explain, you have to explain it, explain whether or not these two alkenes show geometric isomerism. Then the answer is no, they can't show, both of them cannot show geometric isomerism is your final decision, but you have to justify it. Then even though there is a restricted free rotation about the CC axis of the double bond, in both the cases one of the C atoms of the CC double bond has bonded with two identical groups. Here in the printed one, two CH3 groups, in the other one two H atoms. Therefore they cannot show geometric isomerism. Then part C, when dry hydrogen chloride gas reacts with 2-methyl butene, 2 isomeric chloroalkanes are formed. Give the structure of the major product and the reason why more of this form is formed. Here butene, two methyl butene, 2 isomeric chloroalkanes are formed with dry hydrogen chloride. Here it should be dried hydrogen chloride, otherwise there may be unexpected products due to the occurrence of water. Okay, if HCl reaches the pi electron cloud of the double bond, it should reach by directing the hydrogen atom closer to the double bond. Then delta plus hydrogen is there, delta minus chlorine is there. There is a permanent dipole in HCl. Once the pi electron cloud is taken by the delta plus hydrogen, simultaneously HCl bond should be broken heterolytically. Thereby there are 2 possible carbocations formed here. We'll draw them. Here CC now single bond, CH3H, here CH3, CH3. Suppose the H of HCl bonds to the secondary carbon, then the positive charge is borne by tertiary carbon. It's a tertiary carbocation. If the newly arrived hydrogen bonds to the tertiary carbon of the double bond, then a secondary carbocation is formed. Now the positive charge is on the secondary carbocation. The secondary carbocation is less stable with compared to the tertiary carbocation. Since the stability is greater, the higher fraction of the reactant molecules will pass through this tertiary carbocation in its electrophilic addition reaction mechanism. Therefore, the dominant intermediate is the tertiary carbocation. Thereafter, Cl minus will reach the tertiary carbocation, thereby 2-chloro product is formed. 2-chloro 2-methyl 1 2 3 4 butane. 2-chloro 2-methyl butane is formed. Okay. Then give the structure of the major product. Then major product, give the structure. Then you may give the full structure or displayed formula or structural formula. Here 4 carbon atoms are there. 1 2 4 atoms are there. Then in the major product, the tertiary carbon bonds with chlorine. Then it forms 2-chloro 2-methyl 1,2,3,4 butane. Then you have to give the reason. Then under reason you have to say that tertiary carbocation intermediate is more stable than the secondary carbocation. Then reasoning. Yeah, how many? Okay, then you should not limit to the marks given. If you know more, you better write more. There is not any time wastage, negligible time wastage will be there. Then you better say this is an electrophilic addition reaction, or this alkene undergoes an electrophilic addition reaction mechanism with HCl. If H of HCl bonds with the tertiary carbon, a secondary carbocation is formed. If the H bonds to the secondary carbon, a tertiary carbocation is formed. Tertiary carbocation is more stable than the secondary carbocation. Therefore, majority of the reactant molecules will pass through the intermediate, that is tertiary carbocation. Therefore, the major product should be 2-chloro 2-methyl butane. Next one, the major product formed in C can also be formed from 2-methyl butane 2-ol in one step using PCl5. Complete the equation for this reaction. Here again a nucleophilic substitution reaction is taking place. C5 H11Cl is formed. Then HCl will evolve plus POCl3 will be formed. Then these are the products. Then give 2 reasons why this reaction would produce a greater yield of this chloroalkane than the combined reactions in B and C. Combined reactions. In organic chemistry, if we follow more steps, several steps, in each step there may be a wastage of the desired wastage of byproducts. Then we can't achieve or come closer to the 100%. Practically, anyhow, it is difficult to reach the 100%. Anyway, the deviation will be very much greater once there are more steps. Therefore, in organic synthesis, we have to follow the lowest possible number of steps, provided that it is achievable. Here they ask 2 reasons why this reaction would produce a greater yield, because here yield, then percentage yield means the mass of the desired product expected according to the balanced equation.